we model a wave. Okay, we've got a few terms here. The top of the wave is the crest, the height of the wave is the amplitude, and we'll take some notes on that in a little bit. And then this is the direction of propagation, and from any 2 points, that's the wavelength. Any 2 identical points, so from here to the next top would be the wavelength. Okay, now, key learning intentions. Energy is transferred in waves. The family of waves that makes up the electromagnetic spectrum, of which visible light is a small part. Interpret the electromagnetic spectrum and to understand that EM radiation is a transfer of energy without particles. And I've already mentioned that. And there's some key terms here that we're going to look at. But we'll start off by just having a look at these ones here. Now you need to fill these in, by the way. That doesn't have everything there. That's got some gaps at different places. Amplitude is simply just wave height. There's a few words you'll need to learn, but it's not too onerous. Wavelength is the distance between any, we say wave crests, but really it's the distance between any 2 identical points. Now the frequency is the number of waves, if you like, that pass per second. Okay? So that's high frequency waves have many waves pass per second. Low frequency waves, like radio waves, from crest to crest, a radio wave can be kilometres, hundreds of metres or kilometres. Okay? But at the other end of the spectrum, gamma rays, you might get a billion of them in, you know, that same, in a metre. Yes?
Isn't a gigahertz like a million hertz?
Yes. Gigahertz. Megahertz, giga is billion. Did you say billion?
I can't remember million or billion.
It's definitely not million because megahertz is billion.
So it's billion.
Yeah. So that diagram you should have there already. Yeah, the unit for frequency is hertz. Now this part here, you definitely need to highlight. High frequency is high energy, and I'll show you why that's important. But that's the reason why I can stand in front of a radio or a radio antenna, and radio waves are hitting me, and I'm like, I don't care. But you know, I'm immune to them. But gamma radiation, which is at the extreme end, it will kill you. It will penetrate. It can go through a metre of concrete. It's high energy, and so it is extremely dangerous. Now, let's have a look at this. Okay. Hang on. Okay. Now, waves transmit energy from one place to another without moving matter. And what does that mean? Well, look, if I have a slinky, and I do, okay, so we can do a slinky example, but you can understand if I've got the slinky here, and you're holding the slinky there, yes, and I give the slinky a wave, a shake, you're going to feel the slinky move in your hand. But the atoms that I moved don't reach you, do they? Like if I wave this end of the slinky, you feel it down here, but these atoms are still in my hand. But the slinky itself sends the energy of my movement down the other atoms, and it reaches you. Okay? That's a transverse wave. That's just something you'll need to know. This is a longitudinal wave where you give the slinky and it shoots itself along. Yes?
Have you seen a video by Veritasium where they drop a slinky and the bottom stays?
Yes, I use that, the magic slinky, and I get students to try and explain it. Okay. Now, you can have longitudinal waves or transverse waves. We'll see those on the next slide. There's an even better representation of them. But effectively, where are we? Oh, I should have put it the other way around. Because transverse is up the top. Transverse is simply that wave like that. We just go. Keep bouncing back. Longitudinal is when it moves through the length, if you like. So they've just got slightly different properties to them. It's one of those things. You might have to do a play with that later. We'll try that experiment in the stairwell. It's just one of those things that we'll be talking about. There you go. Now, there is a transverse wave, and what they say is this is what perpendicular means, if you like, at 90 degrees. So you see the wave, the actual whatever these are, we can say that we'll call them particles for now, they're moving up and down, but they're not moving forward. The energy is moving forward from one side of the board to the other, just like with the slinky, but each of these is just moving up and down. Now, light waves, we say, are transverse. They don't use atoms or molecules. We say they propagate using photons, which works like a massless particle, I suppose. But yes, you don't need atoms or molecules to propagate light waves, which is very good, because there are no effectively atoms in space. So if that was needed, some light, some heat would never reach us. So we'd just be on a very dark and cold. Well, we wouldn't be here, because nothing would be here. It would be very dark and cold. Okay, so they transfer the energy, but they don't move along with the energy, if you follow that idea. They move at light speed, which is about, it's 299 million and quite a bit. It's very close. So we round to 300 million because, you know, the universe isn't going to have these really neat even numbers for us, is it? But that is the maximum speed of this universe because as you move faster, you gain mass. So you need to have, to go faster, you need to have more mass than the energy.
But
more
there's
mass than the
things that can
universe.
actually go faster, not faster, but as fast. If you get particle accelerators, you can smash gold atoms really fast together.
Yeah, they're still moving, but they still converge at light speed.
Yeah.
And
It's just under, I think.
yeah, but what I'm saying is, if I'm doing 60 this way and I'm doing 60 this way, you'd say it's got a convergence of like 120. Yeah, but it's, you know, there's one physicist. Oh no, I'm not going to say that story. It's kind of interesting, but they reckon they can get a functional time machine thing going. Because if you stir space-time, then you can get the particle these to move. Anyway, 300 million meters per second is light speed. You will need to know that. Obviously extremely fast, so about 6 times around the equator per second. Okay, and so this is quite fast, but of course the universe is a very big place. So the sun is about a little over 8 light minutes away. So if the sun was to vanish, or just, I don't know, voodoo magic, gone, it would be 8 minutes before you noticed, because the actual image of the sun would still be travelling through space for 8 minutes, and then you'd notice. So when you look at the night sky, you're not looking at how the universe is now. You're looking at how the universe was for each of those stars. Some of those stars were gone literally hundreds of millions of years ago, but they're just so far away that the light is still travelling to us. Yes.
Would that mean if you had some sort of like super telescope and you're
Yes.
65 million light years away?
You're looking backwards in time. Yes.
If you
had a powerful enough telescope, you could see the back of your own head.
It must be
Because
mine.
you go right around the curve of the universe.
Yeah.
Okay, now look at this. Ooh, voodoo magic. This one looks clearer. These are longitudinal waves. Take note of the red ones. See, the red one, you can see the energy front moving across the board again, but each of those red ones isn't travelling down the board. Yeah? It's just vibrating in place. It passes that energy on in a big conga line to the next one, and then that passes it to the next one, and passes it to the next one. And this is what's happening with sound waves when I'm speaking to you. This is what your ears are picking up. They're longitudinal. They move at only 340 metres per second, depending on temperature. So some books will say 350, some will say 330. It depends on the temperature. So, which is about 1,225 kilometres per hour. So they're quite slow. Okay, and this is why when you go to the athletics, you'll see the smoke, and then you'll hear the gun maybe, well, if it was 340 metres away from you, 1 second later.
So See the lightning.
Because yes, you'll see the smoke. That's why if you ever do stopwatch duty at the ATS, you look for the smoke. That's when you start your stopwatch. Yeah. Because if you listen for the crack of the gun, you'll be out.
Yeah, they start running and it's like
No,
a second.
No, you're very, very wrong. They're close to the gun,
So after they hear
so
it.
they hear it
Oh.
in real time. I'm far from the gun. It takes a second to travel the 340 meters.
That's
So-
awesome.
So I have to start when I see the smoke. Otherwise, I'm a full second out. Yes.
Mythbusters did a test and they were dodging a bullet.
Yes.
And they had to, they used
Just wait. Now, has everyone filled that in? About the particles oscillate back and forth. So each of these particles is moving. It's moving a little bit, but the energy is moving through. But the actual particles themselves, or molecules, like air molecules, aren't. Okay. Bit of a difference there. Now, I'll show you a nice video of a volcano erupting, and you'll see it erupt. That's fascinating. You don't hear anything
Yeah, it's so far.
because they're so far away. Then you hear something. So Krakatoa, when it went off, what was it? I think we talked about Krakatoa. It's about, what was the distance? I think people 30 and 40 kilometres away, their eardrums will burst. Okay. So from the noise. Okay. Now this is really, really important. So let's get this one right. I've foolishly left my pens next door. This is electromagnetic radiation. Now, look closely. Okay? This is what you call light. You know Royci Biv? Red, orange, yellow, blue, green, indigo, violet? Yes? Fill in Royci Biv. Red, orange, yellow, green, blue, indigo, violet. Fill in Royci Biv right there. What?
It's in black and white.
It doesn't matter. Still fill in Royci Biv. Huh? Red, orange, yellow, green, blue, indigo, violet. White wave doesn't exist. White wave. Okay. Stop. Okay. Stop. Why are the boys' shirts white? Because the sunlight, or this light here, is made up, what we call white light, is made up of 7 colours. Red, orange, yellow, green, blue, indigo, violet. Now, when they hit the white shirt, all 7 colours are reflected. And that's why we see it. If it was red, if it was a red tabletop, the 7 colours, the same white light comes in, but of those 7 colours, only one, if it's a true red, is reflected. The red one, and the other 6 are absorbed. So we'll talk about that a little bit as well. Now, the other thing to note here are radio waves. So radio is a form of light. These are all, electromagnetic spectrum is different forms of light. This is visible light. So for you guys, your entire life, every time you've said the word light, you've meant visible light. But you've never thought of radio waves as being light, but they are. Light moves at light speed. What's light speed? 300 million metres per second. So, Lucy, stop fooling around. So, how fast does visible light move from the sun? 300 million metres per second. How fast do infrared heat from the sun? 300 million metres per second. Radio waves from the sun? 300 million metres per second. Because the sun emits all of those. Okay? These are all forms of light. Okay? Now, they all travel at light speed. Now, what you need to write on your diagram is this. Low energy at this end. This is really low frequency, low energy. And at this end, high frequency, high energy. Okay? Those are the 2 things you need to write. Did you write those down? Okay, now write both of them. Okay? Now, these 3 are important here. Ultraviolet, X-ray and gamma rays. We might emphasise that point now. As I said, I've left my pen behind. But these ones here are ionising radiation. And what that means is they have enough energy to damage DNA. Now, UV light has a fair whack of energy, but it can only penetrate maybe a few skin cells. But that's enough to, if it gets the right, if it knocks out the right gene, your body doesn't repair it, it could cause a skin cancer, where the cell starts to make copies of itself, hits your bloodstream, and then seeds itself. Okay? Very, very dangerous type of cancer. Okay? Now, X-rays, you're familiar with those, they go, because they have higher frequency, they have higher energy. So they can penetrate further. Not bone, but they can go through all your soft tissues. Very handy. But again, they damage DNA. Okay? So the early people who explored X-rays in the early days, not a few of them ended up getting cancer from the exposing themselves to X-rays on a daily basis for years. Okay? Now, gamma radiation, and we'll look at this when we do nuclear chemistry. Gamma radiation is very high frequency. It has 1 million waves per meter, and that will penetrate a block of concrete. So you don't become a superhero, you become soup. Okay. If you get hit with high dose gamma, it's destroying your DNA, it's just fragmenting it.
The worst is when alpha gets into it.
No,
It's
it
the
didn't have to be that
Yes, yes.
How big
Gamma
of
radiation.
concrete can
Meter.
meter? Okay, so it's a meter and 1 centimeter. You'll be
It's
safe.
not exactly like that. Yes.
What is the fine line between visible colours?
Did you write it down?
There is no.
Well, it's a matter of frequency. Like a better table would show, and I do show that when we look at vision, and it talks about those wavelengths. Okay, and look, do you understand the idea? Maybe you've done this prac in junior school where you take maybe a feather, and you get the person to close their eyes, and you touch their elbow, and you see, did you feel that? Did you feel that? And they might go yes, or they might go no. And then you've got the same person and you touch their fingertip. And I think in your experiment you'd find that people's fingertips are much more sensitive to touch. Yes? And this is because the receptors, the nerves in your fingers, are more sensitive to touch. You don't need to have great touch receptors in your elbow. But fingertips, yes. Now, the reason why I'm saying this is your eyes are nerve cells in their own right, the rods and cones. They respond to photons, these things, but only of certain energies. And so that's what we call visible light. So photons of that energy will be enough for the nerve cell to fire and send a signal to your brain. But you get into energies like infrared, you can't see that. Snakes can, okay? Or UV, again, it's not of an energy spectrum that your cells will detect. In the same way that your ears, you can hear certain signals, but then there's other things that you can't hear. They're too high, they're too low. Rainbow shrimp have amazing eyes, so they can see in the UV, they can see in infrared. They're all over the shop. Yes.
Don't they have like 14 cones?
Yeah, it's insane. I mean, when I say they have amazing eyes, they have an extraordinary range of vision. There are humans, not many of them, who have a 4th cone. They're almost all female. So their colour spectrum is enormous compared to yours and mine. That type of person might come in here, and every one of these tables is a different shade of red to them.
How do you find out if you're like that?
You probably wouldn't know, because you just assume that everyone else is doing it. Like, that red that I see is not the same red that you see. It's just that when you were growing up and I was growing up, older people would point and say that was red, so I've learned that's red. Okay, but you and I are seeing different shades of colour. They're quite different shades
Like
of
my
colour.
red could be your purple. And
Colour blindness is pretty common in males, but a lot of males would go through their lives not knowing they're colour blind. They're just like, you know, yeah, like what they would see that shade over there that we say is yellow as being red. They were told that.
That's scary.
So now, okay, let's get through this. The speed of sound in dry air water because the particles are close together. Sound travels really fast in metal. That's why, you know, theoretically you could put your head on a train track and listen to see if a train is coming. Don't do it. But yes, someone tapping on metal, that'll go a long way because there are many, many particles. And it'll travel faster. So even though it's sound will travel at different speeds depending on temperature and depending on substance. Faster in water, this is why whales can have a pretty reasonable conversation. They're hundreds of kilometres apart. Okay? Because they're emitting a fairly loud sound and it's in water. So they'll go from there. Okay, can I change? Should be able to change. There we go. Yes, can I change?
Can you, are we doing the pyramid?
Oh, yeah.
Hang on, there we go. Now,
I didn't get it. How do you get the rose down?
The channel.
Yeah, you were talking 2 seconds.
now,
Sorry, I didn't mean to say it like that. I have. It's just getting a bit frustrated.
Double FD.
okay. Now there's a little bit on Krakatoa on the next page. Krakatoa is rebuilding itself. It's up out of the ocean now. Took a while.
I thought you said that Krakatoa.
Okay. Now, so 1883, 200 million tonnes of dynamite. That's a megaton. So 13,000 times greater than the atom bomb dropped on Hiroshima. The sound of the eruption was heard on the island of Mauritius, 4,563 kilometres away. How long did it take for the sound to reach the island if sound travels at 1,225 kilometres per hour? Give your answer to the nearest second. Off you go.
What?
Work it out.
What? 0.01 of a second.
Write it down.
Big math. Every day.
Write it down. Show it to you.
3 seconds.
That's a lot of damage.
Birdie,
That's a lot of damage.
Roughly about 3 seconds. Closest.
Yeah,
What is this? It's closest to 3 seconds. It's only 3 to 4 seconds. Oh yeah, per hour, yeah. Pretty
I'll give you 60 seconds.
about 3 hours each one. I don't know what it is. No, but it's 3
3
and a half.
No,
Yeah, no,
because 4 is like 4. Whatever that is.
Okay.
That's 3.7.
Not yet.
Down.
Which is
Uh-huh.
no, it's only 3.7.
Yes. Give your answer to the nearest second.
Nearest second, he said.
Okay, so now I can have it.
How much
So 3 hours, so many seconds.
Oh.
What about no
You manage that.
I got the exact number.
number of hours, minutes and seconds, okay?
I don't think
Oh, and seconds.
Hours, minutes, seconds. Couldn't be simpler. Or are you just going to give it to in total seconds?
Yeah.
Total
Okay. It should be hours, minutes, seconds.
Yeah, that's seconds.
Do it hours, minutes, seconds. Okay, listen up. Now, I just want to cover a quick point, because some people say, oh, why are we doing maths and science, which is just the saddest thing ever. But anyway, let's go. Now, if I can walk, now let's do some, look, a lot of people, they see big numbers and they go, oh wow, I'm at a bit of a loss. And they walk. And what I'm saying is this, look, if I can walk at 4 kilometres an hour, and my house is 12 kilometres away, how many hours would it take me to walk home? 3. Is everyone clear on 3?
Yeah.
But using those numbers, how did I get there? And you say, well, I just did 12 kilometres divided by 4 kilometres an hour. Cancel? No, it's 3 hours. 4 times 3. So, no. So, what I'm saying is, what you've done is, you've taken the distance and you've divided it by the velocity. So, here we go, same thing. There's my distance, there is my velocity. You do the same thing again. 4,563 divided by 1,225 equals, is it 3, what's it in decimals?
3.72489.
Hang on, stop, 3.72. Now that's 3.72 hours. Stop, watch carefully.
4 hours.
3 point, yeah, stop. Now, we can't use decimals. And there are 60 minutes to an hour. Okay, so what is 0.72 times 60 minutes? Type that into your calculator. 0.72 times 60, yeah? No, I just want that answer. 0.72 times 60. 43.20.
Yes.
Okay, so it's 43.2 minutes. Now we can't use decimals. So we know we've got 3 hours, 43 minutes, and now we go down to 0.2 minutes times 60 seconds is 12 seconds.
I just took a guess and I was so close. My guess was 3 hours 42:16.
That's pretty good.
I know, I'm actually Sherlock Holmes.
But
I never know that.
But you did the conversion of decimals too.
No.
No,
Okay.
she
I
just
didn't-
had
I
a
just
complete
guessed.
guess.
Okay. But does everyone follow how we worked through that?
Yeah.
Okay. Like you can't, a lot of people that get to like here, they go, oh, 43.2 minutes, that's 43 minutes and 2 seconds.
Huh.
No, it's 0.2 of a minute, which is 12 seconds. Don't mix up units.
It's because you kind of confused me. It lost me at 1 second.
It's 20% of a minute.
Okay, so now this is an equation for wavelengths. Calculating frequency. Frequency is velocity divided by this symbol here means wavelength. So if a wave's wavelength is 10 meters and it's moving at 40 meters a second, what is its frequency? Work that one out. You should be able to do it in your head.
2. 40 minutes per second.
6.
The unit is hertz at the start.
Oh,
40 divided by 10 is 4 hertz. So you get 4 wavelengths effectively per meter. So it's probably a radio wave. Okay, and there's your revision. Okay, so light, type of wave, transverse, this one, transverse, light, all forms of light are transverse waves. Can they travel through a vacuum? Yes. Can they be reflected? Yes. Can they be refracted? Refracted means to bend. Yes. Velocity, 300 million meters per second. Longitudinal waves move through the wavefront. They require, they can only go through a solid or a liquid or a gas, not a vacuum.
Plasma?
Maybe a plasma. Let's see. Can be reflected? Yes. Can be refracted? Yes. 340 meters per second.
You know, why don't you count that last